Hey folks, Todd Coburn here with your Aerospace Structures series. This video is on the macromechanics of a lamina, and now we're focused on strength. So once again, we're dealing with a single layer of composite, and we're going to look at what ways we use to evaluate whether something is strong enough or not. And we can call this also failure criteria. So let's see how it works. So our basic criteria, when we're evaluating the strength of composite, we're looking for a way to evaluate whether or not it fails. What we're doing is we're looking at the principal stresses in the three principal material directions. We're going to have a stress in the one direction, a stress in the two direction, and a shear stress. Potentially any of these can be zero. Our lamina, according to our assumptions that we're going to use, is not able to take bending in and of itself. The way it can help resist bending is by having axial and shear properties in the plane of the lamina, which then, when we use classical lamination theory, will result in a bending capability for the laminate. But each individual layer, we're going to assume is thin enough to where the bending stiffness of itself is negligible. It's only its extensional and shear properties in plane that affect our strength. Our basic approach is going to be then to figure out what are the maximum stresses the thing experiences, or the lamina, or what are the maximum strains, and then we're going to compare those to the allowables. Now we can do this on allowable by allowable basis, or we can use a failure criteria that evaluates the inner reactions of the different stresses on the weaknesses or the strengths of the material. So there are a couple ideas we need to understand. First, when we're talking about orthotropic lamina, the axis of principal stress is often not going to coincide with the axis of principal strain. What does that mean? Well, it means you're going to get your principal stresses aligned with your principal material directions, but the lamina is going to tend to strain a lot more in some other direction where it has less stiffness. Also, we're going to find out that our strength in one direction is often different than the strength in the perpendicular direction, and if those are different, or even if they're the same, we're going to see a change in stiffness, a change in properties for each rotation of the element. That adds complexity. This means our maximum stresses and strains critical stresses and strains could really occur in any direction, and we may need to do a lot more analysis to verify that the part is good. So what we first need to do is evaluate what are our strengths in the material principal directions. And typically, we're going to use those strengths coupled with the stresses in those directions, or the strains, to evaluate failure or lack of failure. Let's take a look once again to make sure we understand what we're talking about. This is a sketch of a typical single lamina, and the sketch on the left says, once again, we've got a couple principal directions, the one direction, the two direction, the three direction we're assuming is stress-free, and the element is thin. The stiffness that our element has, according to our theory that we laid out in the last couple lectures, is it has axial load carrying capability in the one direction, axial load carrying capability in the two direction, and shear capability. It's got no bending capability, either in plane or out of plane, and it's got no stresses out of plane. Okay? No torsional capability. This is shown like the little sketch on the left, and we could also show it like the little sketch on the right, looking down at the two principal directions. It's a 3D and a 2D view. Remember, thinking back to our last lecture, we saw that stresses were related to strains, or 2 lectures ago, through the Q matrix, and the strains are related to stresses through the S matrix, where the S matrix is just the inverse of the Q matrix. Our nomenclature then, when we look at our lamina, we're going to have a principal material direction, the one direction, and we're going to call the strength F F1. This is following aerospace nomenclature, where in aerospace, even though sigma is often used for stresses, and we're often going to use that for stresses here in our composites class, lowercase f is also commonly used in aerospace to designate stress. Capital F, while we thought of that as a force when we're back in statics, when we're talking about aircraft analysis, capital F is typically given to mean an allowable stress. We're going to follow that nomenclature, and we're going to call our allowables capital Fs. We're going to use a subscript 1 or 2 to represent the 1 or 2 principal material directions. We're not going to evaluate the strength in any other direction but the 2 principal directions, because that's typically where we're going to have values, and we're going to be converting our stresses into those material principal directions. So F1 means we have a normal allowable for a normal stress in the one direction. Now, if we're talking about tension, if we have a tension stress, we're going to compare to a tension allowable. We'll give it another subscript T. If we have compression in that one direction, we'll give it a C. So F1T is tension, the tension allowable, stress in the one direction. F1C is the compressive allowable stress in the principal one direction. In the two direction then, our allowable in the two direction will be F2T or F2C. And our shear stress allowable, our in-plane shear stress allowable, is F12, as we see here. So once again, to just write them out, F1T is our tensile strength allowable in the one direction, that's in PSI or KSI. F1C is our compressive allowable in the one direction. F2T is tension allowable in the two direction. F2C is compression allowable in the two direction. And F12 is the shear strength allowable in plane, which is the 1-2 direction. Got that? Okay. So let's just take a moment to think about this. Let's say we have this particular element, and we have these allowables for that element, 50,000, 1,000, 2,000. And let's say we have these stresses applied to that. Will this fail or not fail? Well, if you look at these values, looks like sigma 1 is less than its allowable, sigma 2 is less than its allowable, but the shear stress is higher than the allowable. Therefore, it will definitely fail. How about this scenario? Well, if we look at this, we see sigma 1 is still below, sigma 2 is now exceeding, sigma 3 is not. Since sigma 2 is exceeding, that will fail. Third scenario, with these stresses, we see this now sigma 1, which exceeds the allowable. All three elements fail. If we ever exceed the allowable, assuming these are the real allowables and not some statistically offset value, we will expect failure. Now, it is true that it's possible that because of the other stresses, we could fail at an even lower number, and that's what the failure theories will help us to evaluate. But if we exceed any of these allowable stresses in any of the principal directions, we can expect material failure. All right. So a word here on shear strength of an orthotropic lamina. We saw or talked briefly about how our strength is a function of the orientation of the stresses relative to the principal material axis. Shear strength, however, if we look in the principal material direction, we'll see that whether we have a positive shear, as we're seeing these two pictures from Jones' text, if we have a positive shear like shown on the left, and the negative shear is shown on the right, these are basically going to have the same allowable. Why? Because the shear causes slippage between the layers and shear across the fibers at the same time. Okay? And if we look at that, we see that that element, the leftmost element, is extending like this, which is loading up kind of off at an angle 45 degrees from the fiber. And if we have a negative shear strength, we see it causes the same loading. It's just kind of reversed, but it still is loading the fibers in the same kind of off angle axis. All right? Now, however, if we have any other, so this was for when the shear is aligned with the principal material directions, it doesn't matter if it's positive or negative. But let's take a different, let's say that the shear stress is not aligned with the principal material direction as we see in these two pictures. And we're going to evaluate positive versus negative shear. Well, in the positive shear case, the leftmost case, we see if we rotate that element, that shear stress is deforming the element like this, which is causing tension on the fibers. But now, a negative stress is deflecting it like this, which is causing compression on the fibers and tension splitting the fibers. Those often are completely different allowables. And hence, for this lamina, unidirectional lamina, we would expect to see a different shear strength for positive and negative shear if we have the shear in a non-principal axis. This is just showing some of the complexities of orthotropic analysis that we're going to be dealing with the lamina. Next, let's take a look at our allowables. If you look at your appendix in your handbook, we've got SI allowables and we have US allowables. You see, these are actually for a couple representative materials, and actually within each of these classes of materials, glass epoxy, boron epoxy, graphite epoxy, Kevlar epoxy, even within those you can have a wide range of properties based on how good is your glass, how stiff it is, how strong it is, and what your volume fractions are. So these are just some representative problems that we could encounter. We see we've got the moduli in the different directions, we've got the strengths in the different directions, and so on. So with these allowables from our appendix in hand, we're ready to start evaluating some of the failure criterion that have been projected. First, we're going to take a look at what happens when we load up a lamina, right? We could expect to see, and we have to decide what we're going to call failure. Are we going to call fracture failure? That's pretty much always failure. But some folks want to be a little more careful for different applications, and they may call yielding failure, as we see here in this second picture from Jones. There are often curve fitting approaches where we will plot the sigma 1 and sigma 2 and then evaluate against test data and try and sketch a line around that envelope of potential failures, calling everything inside that envelope good and everything outside of that envelope bad. And while curve fitting can work pretty well with conventional isotropic materials like aluminums and steels, it may not do so well with composites because of all the complexity. In fact, John Hartsmith from Boeing was reported to have said that most failure criteria are meaningless curves passed through unrelated data points. He was a very sharp cookie and quite lively personality, and had done some extensive research into composites. And I kind of agree with him. I also kind of don't agree with him. So on the one hand, while that's true, yeah, many failure criteria are meaningless curves passed through unrelated data points, and in one sense that's complete nonsense. But in another sense, if we actually have enough test data and this curve goes through the failures, it really doesn't matter all that much if they're different failure mechanisms, because if we have done extensive enough testing and if that curve represents the way that that material behaves, regardless of which failure mode is driving the failure, that can be a meaningful way for engineers who need to make decisions and get things done within the current context of modern technology for doing structural analysis. So let's take a look at our failure criterion. So the first failure criterion we're going to look at is the easiest, and it's the most akin to most of what we've been doing up to this point in our first and second structures class. What we're basically going to do is look at each of the stresses. We have sigma 1, we have sigma 2, and we have the shear stress. Remember, no matter what stresses are applied to the lamina, we're first going to convert them into stresses in the two principal directions, which means we're going to have sigma in the 1 direction, a stress in the 2 direction, and a shear stress. And the maximum stress failure criterion just says we're going to look at each against its allowable to find out if we fail. That means we're going to take sigma 1, and if it happens to be tension, we're going to compare to F1T, which we find right here in our appendix. So if we have a graphite epoxy, that's 217 KSI roughly. You see that? If we have if we compare our stress in the 2 direction, if that's tension, we compare that to the tension allowable, and here we find that. Now actually this is a little typo, because these say that these stresses have to be less than this, and that's actually not true. They need to be less than or equal to. Equal to is good enough. Got it? Less than or equal to. It's like max bench press. If you can bench 300 pounds, then you're expected to bench 300 pounds. Your margin of safety is 0. You can get right up to that allowable. Same thing's true here. Okay? For compression, if our sigma 1 is in compression, we compare it to the compressive strength. If our sigma 2 is in compression, we compare it to the compression strength. And once again, we can expect to see this is actually great. This has to be less than or equal to in both cases. Great. Okay. Now, if we have our shear stress, we can compare that to F12, which we're calling in this table, we're calling it F6, following Barbaro's nomenclature. So this also can be equal to and be acceptable given the 0 margin of safety. So we would write our margin of safety is for each one independently, the allowable divided by the stress, the allowable divided by the corresponding stress, the allowable divided by the corresponding stress, each of those minus 1. That's the margin of safety, and that evaluates whether we're failing or not. A 0 margin of safety is nearly optimum. Anything less is a failure, anything more is fat, acceptable. Okay, a couple more ideas. Once again, this approach is assuming there are no interactions between the failure modes. And so our stresses first need to go, remember we're going to evaluate our stresses into stresses in the principal directions, and we're going to compare to these allowables. Okay? And a lot of folks think that this is not sufficient, that we could do a better job. Now the second method is like the first, and what that's doing is instead of checking the stresses, we're going to check the strains. We're going to evaluate each of the strains in the principal directions against the maximum strain, ultimate strain in those principal directions. Some folks say this is a better approach because you have to do a strain basis. I tend to disagree with that idea, but that's what this approach does. Of course, that assumes that you have a strain-based allowable rather than a stress-based allowable in order to do this. Okay? The next theory is called the Tsai-Hill failure criterion, and Hill proposed this criterion with a bunch of constants to relate stresses to potential failure. And this is an extension of von Mises' yield criterion, and he went onward. Tsai came along and related these parameters to the failure strengths and wrote out a failure criterion that looks like this, where we're going to take the stress F1, F2, and shear stress 1, 2, and you'll notice we switched part of this nomenclature to F's, and the other part we left as a tau. This could have been F1, 2, right? Compared to the corresponding allowables. This is his failure criterion, which means we can write the margin of safety in this way for this criterion. Okay? We just plug in our stresses, we plug in our allowables. Now, a couple caveats. When we're using this equation, the allowable and its sign for each normal stress has to correspond with the sign of the applied stress. What that means is if we have a tensile F1, we're going to need positive 1T for the F1 allowable. But if it's a negative value, then we're going to put in negative F1C. So we're including the negative sign with the compression allowable and stress. The same approach applies to F2 for the negative sign. Okay? That's how we would use this failure criterion. So with the Maximum stress criterion, we just check each of the stresses against their allowables. If any of them are negative, it fails. If they're all positive, we expect it will probably survive. With the Tsai-Hill, we plug each of those stresses into this failure criterion, and if the margin of safety is positive, which means 0 or better, it's good to fly. And if it's negative, it's good for redesign. Okay? The Hoffman criteria, he comes along and he postulated this equation where we have 9 principal failure strengths are these C parameters, and if we have plane stress, this simplifies to this value. If we want to write a margin of safety for this puppy, we can write it this way. And once again, we're going to need to be careful with the signs. We're going to include the negative sign with our allowables F1C and F2C, as well as F1 or F2 if they happen to be compressive. Okay? And if these compressive and tensile strengths are equal, then this will convert on back to the Tsai-Hill criterion. Once again, we're going to transform our stresses into principal material directions before doing this evaluation. And this tends to work better for these kind of materials. Okay? The Tsai-Wu criteria proposed this equation, where these are the constants that are used in our failure criterion. Well, it actually, if we want to write this for plane stress, we can write it this way. And in both these equations, A12 can be written as this parameter here. And where the sigma is unspecified and has to be determined by some other manner. Kaw comes along and he suggests 3 alternatives for sigma. You can check out his book on your own. Jones reports that we can just call it 0. Because this sounds like a lot of hocus pocus and guesswork, I don't actually recommend this one. However, if you have test data that shows that this criterion with some assumptions on what that sigma should be matches your test data, then that could be potentially be good engineering. So what we've done is we've looked at a few failure criterions. In all cases, we first have to be masters of our Q, relating stresses to strain, and our transformation to develop what are the stresses and strains in the lamina. While now we're dealing with a single lamina, later when we deal with laminates, stacks of lamina, we're going to first evaluate what the stresses are in each lamina, then we're going to turn them into principal material directions in each lamina, and then we will evaluate each lamina for failure. Not the laminate as a whole, but each lamina, and we'll use a collective result to determine whether the laminate is good. So stay tuned, and we'll be there soon enough. Enjoy.